Section 3.3 is the slope of a line. The three objectives are to find the slope of a line through 2 points, to graph a line given its slope and a point on it, and to identify the equation that represents the standard form of a line and its slope. First, we need to define the term slope. The slope of a line really indicates how its height changes from left to right. So we can see here's the initial height, and as we move from left to right, the height is changing, it's increasing. We call this change in height the rise, and we call the change from left to right the run. So we can consider a skateboard ramp that's viewed from side, so the projection looks like a right triangle here. So we have the right angle right here, and this rises as it goes from left to right. Now, taking a thought about this, you could say that the ramp steepness in that last example would increase if the rise were greater. So we could have our first ramp, say it looked like this, but then superimpose a second ramp on top of it, make believe this is the second ramp now. Well, that ramp in blue is much steeper. So we could say simply that the steepness is another way of saying its slope. Okay, so the ratio of the rise to the run is going to be our definition of slope. So we start with say slope is defined as rise over run. Well, the rise, this change here, is our vertical change. Well, vertically, we say that's the y-axis. So the change in the vertical coordinate over the change in the horizontal component. A lot of teachers always say y2 minus y1 over x2 minus x1. But again, remember that it's the change in the vertical coordinate over the change in the horizontal component. This could be labeled distance, and this could be labeled time. Things change when you look at graphs. So remember, it's change vertically over change horizontally. Rise over run between any 2 points. Now we need to take a moment to classify these slopes. And what we're going to see here is the first example is an example of a line with zero slope. From our last lesson, we'll know that this is a horizontal line which follows the equation y equals some number k. But for the sake of this, let's pick 2 points on this line. It doesn't matter, I'm going to make up points for these. So let's say this point is 7, 8, and this point is going to be, let's say, 12, 8. Clearly they have to both be 8 because they're on the same y coordinate. And if we look at the slope here, my change in y is going to be 8 minus 8, which is 0. My change in x is 12 minus 7, which is 5, and clearly that is 0. Okay, so a horizontal line has zero slope. A horizontal line has zero slope. And think about it, if you're walking along the ground, you would say that there's no incline, or the ground is not steep, it's flat. Okay, but now think about a wall. If you tried to climb a wall, its steepness goes up and up forever. You'll never make it over unless there's a top to that wall, but lines we know go on forever. So this steepness is infinite, really. This steepness goes on and on forever vertically. So let's take a look at what that means. Pick a point here and pick a point here. Let's say this point is, in this case, 14, 12, and 14, 10. Well, change in y is going to be 12 minus 10, which is simply 2. And our change in x is going to be 14 minus 14, which is 0. But you can't define by 0. So we say that this slope is undefined. Okay, and you'll learn in calculus that the idea of that slope is that it approaches infinity. Because the slope is so great, it's such a high number that it's an infinite slope, where its limit is infinite. And you'll hear more about that in calc and pre-calc. Now, the next 2 examples, though, talk about positive and negative slope, and this is a little bit more clear. Remember that slope is defined as the change in height from left to right. So if I go from left to right and start here, my height is changing, it's going up. So I say that's a positive slope. And if I start at the far left and I continue along this line, my line is going down. That's a negative slope. Let's take a quick look at example 1 and find the slope containing the given points. So for part A, remember my formula is change in y over change in x. So I simply have to look at my y's. It's going to be change in y, negative 2 minus 5 all over 4 minus negative 3. Again, this is my change in y, negative 2 minus 5. My change in x is 4 minus negative 3. Negative 2 minus 5 is negative 7. 4 minus a negative 3 is a positive 7, giving us an overall value of negative 1 as a slope. So clearly for this first example in part A, the slope is negative. And I can check that mentally if I draw a quick mental image. Negative 3, 5 is somewhere up here. 4, negative 2 is somewhere down here. This has got to be some sort of a negative slope. Part B, let's look at our change in y. Our change in y in this case is going to be 6 minus 4. And our change in x is 5 minus negative 1. 6 minus 4 is 2. 5 minus negative 1 is 6. 2 over 6 is 1/3. So my slope for part B is 1/3. This again means that the slope is positive for part B, or the line is increasing. Remember a moment ago we looked at a line with a negative slope and that line was decreasing. A line with a positive slope would be increasing. Terminology you need to remember. You're going to use this in pre-calc and calculus. For part C, we'll take a look and we'll notice here that our x-coordinates are the same right away. So something weird is going to happen. So it's going to be negative 11 minus 4 over 2 minus 2. The numerator doesn't even matter. It turns out to be negative 15, but it makes no difference at all because it's over 0. So this slope is undefined. Okay, remember that this is a vertical line. Let's take a look at a theorem here, and the theorem says the following. The slope of a line in the standard form ax plus by equals c, where b cannot equal 0, is equal to negative a over b. Negative a over b. Remember, b can't be 0 because b is in the denominator there. So, that's the theorem. Let's go to the proof of this theorem. So if we say that x1, y1, and x2, y2 are two different points, but they're on the line ax plus by equals c. Well, we could say that if we have 2 points, the slope between them is, again, y2 minus y1 over x2 minus x1. So what we can do is, we can take these points here, okay, and plug them into this equation right here. And if I plug x1, y1 into here, I have ax1 plus by1 equals c. That's the first line. If I plug in the second coordinate, I get a x2 plus b y2 equals c. That's the second line here. Now, what we're going to do is combine these two equations by subtracting the first equation from the second equation. Okay, the first equation from the second equation. This is a type of linear combination. So if I subtract the first equation from the second, I end up having ax2 plus by2, first equation, minus the second, ax1 plus by1 equals c minus c. So again, I'm thinking of this like a subtraction problem. Okay, I'm thinking about it as a subtraction problem. I happen to be doing the second equation minus the first one now. C minus c is just 0 over here. Well, on the left-hand side, I can go ahead and rearrange my terms. ax2 minus ax1 plus by2 minus by1. How do I know this? Well, remember, this negative sign gets distributed to both. So the x1 and the y1 have to have negatives in front of them, and they do. The ax1 has a negative in front, and the by1 also has a negative in front of it. Well, then what we can do is we can notice we can factor out. Factor an a out of the first term. Factor a b out of the second term. And at this point in time, we'll notice that we can move things around. So let's go ahead and move the component that has the a part over to the right-hand side. So let's subtract this entire thing over here, giving us b parentheses y2 minus y1, which is left over, equals negative a x2 minus x1. Again, by subtracting this entire term right here over to the right-hand side. And now what we'll notice is that we can simply divide by x2 minus x1 over here. And we'll see some similarities to our slope equation already. These cancel. And then go ahead and divide by b on both sides. Cancel, cancel. We end up with just the slope here and negative a over b. Exactly what we were looking for. So slope in standard form is negative a over b. Again, this is a proof of where it comes from, but I'd like you to apply this proof. What you would also notice is that if you were to solve the equation ax plus by equals c, if you solved it for y, so again, solving the original, If you solve this for y, you get y equals negative a over b x plus c over b. Go ahead and try that. Solve generically for y. And what you'll see is that here's the negative a over b, here's the negative a over b. And this is a little bit of a correlation. We'll notice that the coefficient of the x term turns out to be the slope. And we'll see that in the next section in 3-4. So example 2 says, find the slope of a line given by the equation 2x plus 3y equals 5. Well, you don't even have to solve for y. If it's in standard form, use your standard equation. Slope equals negative a over b. So it's simply negative 2 over 3 or negative 2/3, which is our slope. You could check this by solving for y, and the coefficient in front of x would be negative 2/3. Example 3 says, determine if the following given points whose coordinates are listed in the table lie on a line. If so, give the slope of that line. So it's a little interesting to look at this one. You can graph this and see if it makes a line, but we can analyze it mathematically. We'll see that the change in x here is 1. All right, every one of these changes in x is 1. So if I remember slope, well, slope is defined as the change in y over the change in x. So the change in x is 1 for all of these. What's the change in y? The change in y is down 2, down 2, down 2. So that's a consistent change in y of negative 2. So it means that the slope in this problem is simply negative 2. Again, every change in y of negative 2 produces a change in x of positive 1. In part B, we'll see that the change in x is up by 2. That's good. And the change in y in this case, it seems like it goes down 3, up 3, and then up 3. So we're going to see right away that this is a bit of a different problem. So the change here is not constant. So there's no consistent change at all. So there's no value I can put here because there is no change in y that's consistent. So because there's no consistent changing, this is not a linear example. And to show that, let's take a look. Here's 0, 3. Here's 2, 0. Here's 6, 3. And then here is 8, 6. So we see that we have, it looks like, a function that goes down and then back up. And we'll talk more about what that function is a little bit later in here. Keep that shape in the back of your mind now. And then for part C, let's take a look. For part C, we're going to see that the change in x, it goes up by 1, but then it goes up by 2, but then it goes up by 4. So my increments are doubling here. So at first, it seems like it's a little bit confusing. But take a look here. This increment goes up by 2, then it goes up by 4, then it goes up by 8. So the increments are also doubling. So let's look at this one a little bit further. Let's zoom in here and see what we want to look at here. Okay, so for this part, we're going to see that this goes up by 1, then up by 2, then this goes up by 4. This changes up 2, up 4, and then up 8. So what we'll notice is that when there's a change of 1, there's a change of 2. So the y change is double the x change. Well, here again, look, the y change is double the x change. The y change is double the x change. So for these problems, whatever you have for a change in y, it turns out that whatever this number is up top, it's twice as much as the change in x. So what's the slope? The slope is 2 over 1, or simply 2. And you can go ahead and graph these to see that the slope is indeed 2. All right, this problem is really interesting. What do you know about the values of a and b if the line ax plus by equals c has the property described? Let's take a look at each of these individually. If the line is horizontal, well, right away, remember, horizontal lines have no slope. They have absolutely no slope. And we know that slope is negative a over b. So if the slope here, again, sorry, zero slope, I should say, really, because again, no slope is like undefined. But there's zero slope here in this problem. So because there's zero slope, it means that the numerator must be 0. The denominator can be anything, really. So if the numerator must be 0, we know that a must equal 0 for part A. But for part B, we know that the line is vertical. The line can only be vertical when the denominator is equal to 0, or the slope is undefined. So in this case, negative a over b, we know that the denominator must be 0. The numerator can be any number. Okay, so the numerator could be any number, but the denominator must be 0, therefore b must be 0 for part B. For part C, it says the line rises from left to right. Let's take a look at what that means. A line that rises from left to right looks like this, which means that the slope must be positive. M is greater than 0, the slope is positive. Well, if the slope is positive, and we look at this right here, we know that A and B have to have opposite signs. Because if I think about this, how would I only get a positive slope? Well, B could be negative, and then I would have, say, like, let's say A is 2, and then B is negative 5. We get negative 2 over negative 5, because remember, this negative sign is this one here. So A is positive 2, and B is negative 5. If I get a negative over negative, that's a positive. So clearly, A and B have to have opposite signs. I could also switch it. What if B was positive and A happened to be negative? Well, then I end up getting a negative negative in the numerator, which is a positive, over a positive. So this would still give me a positive slope. So in order for there to be positive slope, A and B have to have opposite signs. For the line to fall from left to right, we're looking at an example like this for part D, which means it's got a negative slope. And if you have a negative slope, that can only occur if A and B have the same sign. Again, this negative on the outside is always going to be here. So if A and B are both positive, then I've got a positive over a positive, but this negative here makes the slope negative. So A and B have to have the same sign to make this overall quantity negative, to make the slope negative. So for part D, we could say that A and B must have the same sign. Example 5 says to graph a line that has a slope of negative 2/3 and goes through the point negative 2, 4. So let's go ahead and take a look at our axes here. Start by labeling. There's our x-axis, there's our y-axis. It looks like I'm going to only go to negative 2, 4, so I can go by ones. So if I just put a simple 1 here and a 1 here, I'll know that I'm going by ones on both axes. So negative 2, 4 is the point right here at that intersection. And my slope tells me is negative 2/3. So it means that my rise is going to be negative 2 and my run is going to be 3. So I go down 2 over 3. And I put my next point right there. So here's my starting value. So I'm going to go down 2 and over 3. That brings me right here. If I look again, negative 2 and then positive 3. Now I can take this negative sign and apply it to the denominator. So I could say go up 2, but then go left 3. Same difference. So I go up 2 and left 3, puts a point up here. So I can either think of the numerator or the denominator as my negative coordinate. It doesn't matter as long as one of them is negative, and a negative slope must fall from left to right. So when we graph this, we're going to see that clearly there must be a negative slope at hand for this problem. Okay, my graph's a little bit weak there for my line, but again, that's what we're going to look like for our line. Again, with a negative slope, it's falling, and it goes through the point negative 2, 4. Remember that for this problem, what we're really looking at is the change in y. This goes down 2, and then positive 3. Or this goes positive 2, and then negative 3. So again, change in y here would be negative 2, but then a positive 3 for x. Or change in y would be a positive 2, but then negative 3. Negative 3 for your x. Either way is fine as long as you end up with a line that goes down from left to right. Example 6 says, on your calculator, plot the family of lines y equals ax, where a could be positive or negative half, positive or negative 1, positive or negative 2, positive or negative 4. And here's what you're going to notice. Okay, here's what you're going to notice. Let's take a look at our graph here. We're going to see in general, when you graph these, that y equals ax with a slope of, say, 1 looks like this. That's our basic line with a slope of positive 1. And what we'll notice is that for all slopes greater than 1, like 2 and 4, the slope seems to increase. So this would be like 2x, and this would be our 4x. And again, I'm just sketching right now, so it's a little bit off. And then when we have a slope that's a fraction, we're going to see that our slope is a little bit less steep. The slope of y equals 1/2 x looks like the following. And I'm not even continuing these lines into the negative quadrant, so we could ignore this just for now, just to see the idea. So those would all be slopes with positive lines. This is like our basis that we're comparing everything else to, though. This is our basic y equals x line. The minute the slope's value gets greater than 1, we see that the line gets steeper. When it becomes a fraction, it gets less steep. And we're going to see the exact same thing, but with the negative slopes, it's going to be a reflection over the x-axis. So y equals negative x looks like this. Okay, that's our basic line, y equals negative x. Again, I'm not continuing off into the other quadrant, but this would really continue over here, but I'm not worrying about that now. Now here we're going to notice that Negative 2x gets steeper still, but steeper in the negative direction. And negative 4x gets even more steeper. And more steep. So we have negative 4x for that one, and y equals negative 2x for that one. And for y equals negative 1/2 x, we'll notice that that's even less steep. Okay? So once again, when you see a fraction that is a proper fraction like 1/2, not something like 7/2, when you see a fractional coefficient that's between 0 and 1, or in this case 0 and negative 1, either one of these, it's going to be some line that's not very steep. But when the coefficient of the slope becomes 2 or 3 or 4, it means it's getting steeper and steeper and steeper until it became perfectly up and down, which is vertically steep. So we called that vertical line. Remember, the slope was undefined, but really it just means that the slope is getting bigger and bigger and bigger. So imagine the slope becomes infinity. That's a vertical line. Okay, a vertical line. Your homework for this section is from section 3.3.